Hello, welcome to the next tutorial of analog circuits. I am your new TA Shashank Tiwari. In last tutorials you have seen problems related to simple op-amp circuits, phase margin, gain margin and all those things. Now in this tutorial I will be dealing with filters, which are the essential components in analog circuits. So as discussed in theory, sir has taught two kind of filters, basically covering low pass filters. These two filters are Butterworth low pass filter and Chebyshev low pass filters. So there is an entire design methodology for these filters. So I will be taking one problem in which I will be designing the Butterworth filter of some n order, that we will see what is the order of filter and then realize it and plot it, just to realize that how does it come out. So directly getting to the problem is design a Butterworth low pass filter with the following specification. Just to remind you, I will draw the magnitude plot of the filter. So as discussed in the class, there is a pass band edge omega p, there is a stop band edge omega s, this is what we call A max. A max is the attenuation of DC gain at omega p. This is A min. A min is the DC gain attenuation at omega s. So we have been given a specification in the form of omega s, omega p, attenuation at omega p, attenuation at omega s. So the given omega p is omega p equal to 20k radian per seconds, omega s equal to 50k radian per second, A max equal to 2 dB, A min equal to 24 dB, and the absolute DC gain we need to achieve is 4. These are the specification given to design a filter. We need to first find out the order of filter, then we need to go back and find out the poles of filter, then after finding the poles of filter we will be going back and seeing how to realize in hardware in terms of op-amp circuit with RC components. I am solving this question. So this is the question. So I will be elaborating step by step how to solve this problem and design a filter. As discussed in the class, there is a magnitude response of Butterworth filter, which is given as T j omega mod equal to k upon under root 1 plus epsilon square omega upon omega p raised to power 2n, where n is the order of filter, k equal to DC gain. As given in this specification that at omega p A max is 2 dB. At omega equal to omega p, the DC attenuation is 2 dB. Which means 20 log k upon under root 1 plus epsilon square omega p upon omega p raised to power 2n equal to 20 log k minus 2. So from DC gain it is attenuating 2 dB, so the net gain would be 20 log k minus 2 in dBs. Going to next line. So after solving all this, we find out that this epsilon square comes out to be 10 raised to power 1 by 5 minus 1, which gives epsilon equal to 0.764. So we have found out the epsilon, so one variable has been found out. Now we need to find out the order of filter, that is n. So again we have been given a specification here that at omega s equal to 50k radian per second, A min, which means the minimum attenuation should be 24 dB. So step 2, finding the order of filter. So we have been given 20 log k upon under root 1 plus epsilon square at omega equal to omega s upon omega p raised to power 2n equal to 20 log k minus 24 dB. After calculating this and arranging the terms, we will find out that the value of n would be 3.3. As we know that the order of filter cannot be a fractional value, it should be the integer number, either it should be 3 or 4. Since the minimum requirement is 3.3, which means we need to over design the filter. So I am choosing the order of filter as 4. So taking the order of filter as n equal to 4. As we know that the poles of Butterworth filter lies on a circle. So where the radius of circle Rd equal to omega naught equal to omega p 1 upon epsilon raised to power 1 by 4, where 4 is the order of filter and omega naught equal to the 3 dB cutoff frequency. So as discussed in the class, this circle will have 8 poles on it, like 8 poles on it, and all these poles will be equally spaced. This drawing doesn't look like it is equally spaced, but the angle between two consecutive poles is pi by 4. Since we are having formula of angular separation as 2 pi by 2n. So this is the pi by 4 is the angular separation between two poles in this case. Now let us see what are the angles we are having here. Before going further, let me tell you that there are two kinds of pole, that 4 poles are on left hand side y axis and 4 poles on right hand side of y axis. So for a real stable system, we want always poles on the left hand side of y axis. In the next discussion, I will be focusing on the poles on the left hand side of y axis, because the poles on right hand side of y axis belongs to the conjugate of same transfer function. So I will be dealing with the transfer function, not with the conjugate of transfer function. So I will be taking into account the poles on LHS. So there are poles on LHS, those are P1, P2, P3, P4. Talking about the angular separation between two poles, since it is the angular separation, as I told, is pi by 4, that is 45 degree. So from this negative x axis, this will be half of pi by 4, that is 22.5 degrees, and this will be 45 plus 22.5 degrees. These angles are from negative x axis. So from this diagram we can find out what is the P1, P2, P3, P4. So P1 equal to omega naught minus cos 67.5 plus j sin 67.5, and we know it that P4 is complex conjugate of P1. So P4 would be P1 star, that is complex conjugate, equal to omega naught minus cos 67.5 minus j sin 67.5. Just to remind that this radius is omega naught, and omega naught equal to omega p 1 upon epsilon h to power 1 by 4. Theoretically we know the values of these poles. So now P2 is omega naught minus cos 22.5 plus j sin 22.5, and P3 is complex conjugate, so it is omega naught minus cos 22.5 minus j sin 22.5. So these are the pole locations. So half of the things are done. Now the things are left that using these poles we need to find out the transfer function of circuit and then realize the circuit, realize the real circuit with the help of op amp and R and C's. So now going to next step. In the class we have been briefly discussed about the second order filters, but to solve the problem further I would like to discuss this second order filter, general transfer function of second order filter, that is Hs equal to H naught minus H naught omega naught square upon S square omega naught q S plus omega naught square. So this is the general transfer function of filter. Now as we know it that these poles are existing in complex conjugate form, like P1 P4 are complex conjugate of each other and P2 P4 are complex conjugate of each other. So if we are having to realize a second order filter with complex conjugate, then assume this scenario that there is a pole of the filter which is minus alpha beta and there is a complex conjugate of this, that is minus alpha minus beta, and then this distance will be alpha, this will be beta. So we can prove it as the alpha equal to omega naught upon 2q and beta equal to omega naught under root 1 minus 1 upon 4 q square. This relation you can prove from this arrangement. So we have found out that the order of filter is n, that is n equal to 4, and we are having a second order transfer function, that is Hs equal to this. So how to realize a filter which is having higher order or higher order, that is more than 2. So in our case we will be saying that okay, we are having 2 filters, so we will just cascade 2 filters, 2 second order filters and make a fourth order filter. We need to realize fourth order filter, but we have a second order filter. So to make a fourth order filter, cascade to second order filters. Suppose we are having 2 transfer function of two filters like H1s and H2s. So the overall transfer function of that cascade system will be Hs, that is Hs equal to H1s into H2s. So we will write it like this: if h1 s equal to minus h01 omega naught 01 square upon s square s into omega naught 1 upon q 1 equal to omega 1 square is 2s equal to minus 2 omega 02 square upon s square s omega 02 upon q2 plus omega 02 square, where q1 q2 are the quality factors of individual filters and omega 01 and omega 02 are the 3 dB cutoff frequency of filter. So the cascaded system will have hs equal to h1s into h2s. So this is the basic of our cascade filter. So we will design two filters, two second order filter, and cascade it to find out the overall hs of it. We have find out the poles of system, that is p1 p2 p3 p4, and then now we need to realize it. So how to realize it? What are the ways in which we can realize this system? So for that we need to take a second order filter. So I am taking a second order filter from textbook, then I will find out the component values to realize my specifications. We are taking the following circuit, following known low pass filter circuit. This is the circuit I am taking for my filter realization. So I know the transfer function of this circuit, which is VLP S equal to VLP S upon V in S equal to minus 1 upon R in R1 C1 C. This is RA. Upon S square 1 upon RC S upon 1 upon R1 R2 C1 C. So comparing this with a standard second order filter equation, that is minus h naught omega square omega naught square upon s square omega naught q s omega naught square, we find out that h naught is DC gain equal to R2 upon Rn, omega naught equal to 1 upon under root R1 R2 C1 C, Q equal to RC under root R1 R2 C1 C. This is the comparison with our taken circuit. So now we need to find out the DC gain. From the specification we are given DC gain, so we will putting the values here and there and find out what is the values of R1 R2 C1 C and design our filter. So I am stopping here. I will be continuing this problem in the next video.